now being recorded.
Okay, I guess we're going to start with the definition of several types of stability. So the first one is Lyapunov stability, and essentially we'll be classifying the stability of fixed points for now, and then we'll generalize to things like invariant sets. So yeah, you know what a fixed point is? It's just somewhere where the derivatives are zero. So a fixed point, say x naught, is Lyapunov stable if for all epsilon greater than zero, you can find delta greater than zero such that if you're within a radius delta of the fixed point, that implies that your flow will converge to, well, not converge, your flow will be within a radius epsilon for all time t greater than zero. So if I, start with something that's sufficiently near to the fixed point, then if I go forward in time, I stay arbitrarily close. So this is kind of a one-dimensional picture with, you can imagine time is going horizontally, flowing forward in time towards the right. So let me just get a pointer. Yeah, so here I've started within delta. Notice that I might not stay within delta. There's not even a condition for convergence. For Lyapunov stability, you just need to say that if you start within delta, then for all forward time, you stay within epsilon. Yeah, so that's the pictorial thing. And so, for example, you might have seen the limit cycle, which is sort of, well, what it sounds like. It's a cycle that is also the limit of a flow as time goes to infinity. So yeah, here we have a fixed point in the middle. We have a limit cycle at radius epsilon. And so yeah, in this case, delta can be anything between 0 and epsilon, because clearly if we start inside of this limit cycle, since the fixed point here is an unstable focus, we're going to go outwards until we hit the limit cycle, and then we're going to be trapped there, which is an invariant set, and we'll talk about that later. Yeah, also notice that the periodic orbit is quasi-asymptotically stable, which we'll talk about now, and that will make more sense. Yeah, so this is the second type of stability, and we have that a fixed point, say x naught again, is quasi-asymptotically stable if, and now we just need that there exists a delta, such that if we start within a radius of delta, then the flow now converges to the fixed point eventually. So in as time goes to infinity. You can think of this as if we start sufficiently close, then we will eventually converge. Yeah, this is just one example of what the behavior might look like in one dimension. And an example of a flow like this would be a stable focus inside a limit cycle. So anywhere within the radius where the limit cycle lies, call it delta, if we start inside of this, then we will go away from the limit cycle and towards eventually converging to the fixed point. So we will explore why this is also asymptotically stable later, well, very soon. And this is just another more general example of what it might look like, because we don't have to stay within this radius delta. The definition just says that eventually we converge to the fixed point. So there's no limits on where the flow can go, except that it has to end up at the fixed point and stay there eventually. So for example,
in that second example, the one that is that you've written that is just QAS, is that example also Lyapunov stable? Like if you just draw a bigger circle, so like both the examples you've given are both Lyapunov.
Yeah, because if I drew like a circle like this with epsilon, then yeah, this would be Lyapunov stable.
Okay. So can you have like one of these but not the other, like this one but not Lyapunov, or the other?
Oh, hold on. Is this Lyapunov stable? Not necessarily. No, not necessarily, because Lyapunov stability says that for all epsilon greater than 0, you can find a delta such that you start and delta you stay within epsilon. So for example here, right, if I drew epsilon like this, this might not work. We don't, like, the picture doesn't give us enough information about the flow to determine whether there is a radius that we can start in such that we stay within epsilon. I mean, it may well be Lyapunov stable, but given the one trajectory we have, we can't say that it is.
Okay, so is it the case that Lyapunov is like stronger, or like it's harder to be Lyapunov than the other one, or are they kind of like disjoint?
I think they're just disjoint. We'll actually see very soon. Asymptotically stable is the strong one. Lyapunov and quasi-asymptotically stable are, I would say, disjoint.
Okay.
Yeah, because I mean they're talking about different things, right? If you think about it, Lyapunov says something about the behavior. Lyapunov says something about the behavior for all time. So at any time, you will always be in this place. Whereas quasi-asymptotically stable only tells you, where you end up eventually. It doesn't tell you about any of the behavior in between. So I guess they're just completely disjoint things. Yeah, good question. So I guess the point with this was with quasi-asymptotically stable. Yeah, you were choosing a delta. You're choosing a delta such that if you start within that radius, you can do anything in finite time as long as you eventually converge to the fixed point. So to be even more exaggerated, I could go like off the page and come back over here and then go back there.
Yeah.
As long as that's as t goes to infinity. Yeah, and sometimes we might have very, very, very slow convergence. We can have different speeds of convergence to a fixed point. And I think if you do some analysis stuff, you can see kind of what the order of the speed of convergence is, but that's for later. Yeah, so next one is asymptotically stable, or we abbreviate it as AS, and this is basically, as it says, if it's both LS and QAS, then it is AS, and that's just the definition. So this is the strongest stability that we have in the course. And so it basically tells you about the behavior for all time, as well as the behavior, like the convergence behavior as time goes to infinity. So I would say if you start sufficiently near, then you will stay arbitrarily near for all time, and you will also converge to the FP as time goes to infinity. So this is the picture for that. Okay. Does that all make sense? Kind of.
Yeah.
So three types of things. And I think that was all clear. Okay, so the next thing is, I guess, slightly a tangent, but it's necessary for the next bit. So we're no longer really talking about stability. We're just defining things called homoclinic and heteroclinic orbits. So orbits are kind of intuitive. An orbit clearly is, something where you go around something. It has kind of the idea of periodicity or something, returning to a point. Homoclinic orbit, as the name suggests, involves one fixed point. So it usually looks something like this. It doesn't say this in the lecture notes. I'm not sure if it was mentioned in lectures, but this fixed point is usually going to be a saddle point. I'm not sure if that's always, but in general, it's a saddle point because it's going to have this behavior where you, in one direction, it's unstable. You go away from the fixed point and you come back in the other direction. So this forms a homoclinic orbit. If you want to look at the mathsy stuff, it's basically defined as there is some point y that is not the fixed point, such that it doesn't matter whether you go forward or backward in time, you will end up at the fixed point. Because clearly it's just like, it's a directed loop, and if you reverse time, you go the other way. So either way, you end up at the same fixed point. It's all good. Usually it's a saddle. The second one is heteroclinic. So this now involves two fixed points. And the difference is, now if you run time forwards, you end up in a different fixed point than if you run time backwards. Yeah, so it might look something like this, where if there's a y such that if I go forwards in time, I go this way along the heteroclinic orbit, and I get to x0. But if I run time backwards, then I go the opposite direction and I get to x1. Does that make sense?
Yeah, this is logical.
That's very logical. Now we're going to extend this idea of heteroclinic orbits to a heteroclinic cycle. So this orbit thing, I mean, it doesn't look very circular. It's not your typical image of an orbit. I guess it's an orbit because you're kind of staying on this line, no matter where you go in time, you're somewhere along this line. So it's not an orbit in the sense of, it's circular. But yeah, it's an orbit. The cycle, however, this is actually kind of circular. It's a closed sequence of heteroclinic orbits. A quite typical example is this, where instead of just having the one direction, you also have the backwards direction. And depending on where you start and whether you go forwards or backwards in time, you could end up at either fixed point. So if I go y0, then I have a y1. If I go forward in time, I get to x1. If I go backward in time, oopsie, then I will go to x0, and the same thing here. Yeah. So now this is a cycle, but the thing to be aware of is it kind of looks like it's just like an orbit, like a periodic orbit. It's not, because remember that once we get attracted into this fixed point, we stay there. Even though there's an arrow coming out of it, as soon as we hit the fixed point, like if we are actually on the heteroclinic cycle, then when we hit the fixed point, we stay there. It's only when we perturb slightly away from it that we get like the cycle behavior, which we'll see later. We may or may not get cycle behavior.
I have to ask what, because I'm not sure what a periodic orbit is yet. So if you have like a very brief explanation.
Oh, okay. Well, a periodic orbit is, well, it's what it sounds like. It's a closed loop that is an invariant set, which I'll later define to mean, if you start in the invariant set, you stay in the invariant set as time goes forwards. So a PO, right, it's going to be something like this. Yeah, it does exactly what you would expect it to do. If I started here, then like as time goes forwards, I go here, and then it goes like here.
Yeah.
So for example, this might be x0. This could be the thing at t1, and this could be the thing at t2, and so on. So this notation is just saying phi is the trajectory of a point, and so I'm just saying where the point ends up at different time intervals. So I guess the point of a periodic orbit is there's a period as well. So there's a fixed time for you to come back to a point when you start at the point.
Yeah. So is it the case that the period is the same for all points on the orbit, or does each one kind of have its own period?
I believe they should all be the same if you think of it as an integral, right? Because you have to integrate over the whole half of the whole orbit for any point you start at to get back to that point. So I believe it should just be the same time.
Yeah, okay.
Same period for any point.
Okay.
Yeah. I'll remove that now. Yeah, so now we'll look at kind of an example of a heteroclinic cycle, and I think this illustrates it quite well. I've actually picked this example myself. So this is the undamped pendulum in this kind of simple harmonic motion. This is what the phase portrait looks like, roughly. I mean, I haven't drawn in the axes. You can imagine this is kind of the x-axis, and this is kind of the y-axis, and so on. But I'll just remove those because I don't think they really contribute. Yeah, so in an undamped pendulum, you would suspect. I mean, what would you expect? You would think, if I start the pendulum swinging at angle theta, then it's going to swing to minus theta, back to theta, and then to minus theta, and just keep doing that forever because there are no dissipative forces at work, right? Yeah, and so what do you think would happen if you... Sorry, no. So what I just described is the green case. So these green lines where the pendulum just swings around and around like this. And so...
Right. Okay,
you can
because
imagine-
energy has been conserved there, so we get centers.
Yes, exactly. So it's a Hamiltonian system, as you can tell, because like everything here is either a saddle or a center. Well, I guess technically like this isn't. I'm not actually sure about why. Oh no, sorry. A Hamiltonian, yeah, obviously. So a Hamiltonian system means that any fixed point is either a saddle or center.
Yeah.
And yeah, clearly this doesn't correspond to a fixed point. Okay, fine. Yeah. For the black bits, that's actually what happens when the pendulum starts at, it's upside down vertical. And because there's no dissipative forces, it swings all the way around by 2 pi radians and ends up in the same position. And then it keeps doing that. No, sorry, it doesn't keep doing that. What am I talking about? Yeah, if I'm at the fixed point, right, nothing actually happens.
Yeah.
If I perturb like very, very slightly away from the upside down vertical, then yeah, something will happen. It will swing back to negative of that angle. But yeah, funnily enough, in this diagram, we're saying that if we started with the pendulum being upside down and vertical, then it would just stay there. But if we perturb it ever so slightly, then it is unstable.
Okay. Could you draw a quick pendulum with like the angle to the vertical and label some of these points with like what angle they're?
Oh, these. Well, I can just label what these are here. So this, for example, would be minus pi. Okay. This would be 0, pi, and so on.
Okay, yeah.
So clearly this is 2 pi periodic because if your pendulum goes around by 2 pi, it's exactly the same as 0. Yeah, so you get the point.
Okay, nice.
And for the blue bits, this is where I think it's interesting. So again, your energy is being conserved. The blue bit basically is your pendulum has so much energy that it's just going to keep swinging around and around and around forever. As in, it completes more than one full revolution. Because as you can see, if we just like follow one of these lines, for example, it's going to start here at, the angle being minus 3 pi, and it's going to go to minus 2 pi, minus pi, 0 pi, and it's just going to swing around and around forever.
Yeah.
So that's what the blue lines are. And I think if you go really, really high energy, so if like I drew this all the way up there, then you just get like a straight line, which is just, it has a constant speed because the speed is so high. So it's basically approximated by like a, it's just spinning really, really fast. So fast that the speed basically looks constant. Yeah. This is a bonus example. I could not draw this, so I had to get a Google image. So this is a damped pendulum. It looks quite similar, but an interesting feature of this is that the system was no longer Hamiltonian because energy is not being conserved. And that basically, in this case, not always, but in this case, it destroys the heteroclinic orbits, heteroclinic cycles, and it also destroys the periodic orbits inside. Basically, it's showing that a small perturbation on this system would lead you to spiral into this fixed point, which is now a stable focus. In other words, your pendulum stops swinging at theta equals 0, or a multiple of 2 pi. Yeah, and then, well, if you're high energy enough, then you'll follow along, say, one of these wavy lines. And that means you are completing more than one full revolution, but the energy is decreasing, and so eventually it's going to join one of these fixed points by spiraling in.
Yeah.
Yeah, so I think that was pretty cool. Yeah, I've already said that, so fun. Moving on. So we're going to generalize the stability definitions now, and I think that makes sense because, we've just been talking about orbits, cycles, and I've mentioned invariant sets a few times, so it's time that we define them. So just like a fixed point can have a stability or, be unstable, you can also similarly classify the stability of a set. We'll look at invariant sets, which, as I said earlier, is something that, if you go forward in time, you'll stay in that set. In fact, it's a minimal set. Sorry, I forgot to say it was minimal.
Oh, right, yeah.
Yeah, like as in, if you have an invariant set, you shouldn't be able to add something to it and still be invariant, as in the point that you added wouldn't be revisited. So yeah, just don't include it. Yeah, so we're going to start with kind of a definition. Kind of like, I think this is like the delta neighborhood of lambda, which we use to denote the invariant set. So it's exactly what you would think it is. It's just got some clumsy notation. It just means, for example, if I have this invariant set, which is just this periodic orbit, that, well, the delta neighborhood is the collection of all points x such that I can get to a point on the periodic orbit, like in delta distance. I probably explained that worse than the actual definition, but I think you get what I mean. Yeah. And we're also going to say this. So we're going to say that the the flow tends to the invariant set lambda if if the smallest distance between any point y in the invariant set and the flow as t goes to infinity tends to 0. Again, the mathematical notation is probably better than what I said. But yeah, it's exactly what you would think it is. It's just that this definition is sometimes useful if you want to show mathematically that something tends to an invariant set. Yeah, I think this is probably better explained. So yeah, the flow tends to the invariant set if the minimal distance from the trajectory to a point in the invariant set goes to 0 as time goes to infinity. So this is an example. It's a limit cycle. A limit cycle is kind of what can be like a periodic orbit that is, for example, attractive. So if we start inside of the limit cycle, we're going to spiral outwards and essentially tend towards it. And if we start outside the limit cycle, then we'll spiral inwards and tend towards the limit cycle. So in this case, in this kind of neighborhood that we've drawn, the flow of any point tends to the limit cycle.
Yeah.
Okay. Now we're going to do a few examples of stability classification. Hopefully we do them now and then you never do them again because you can just quote this in exams. So for a stable focus, for example, we can easily draw this delta circle and we can see that if we start within delta, then we converge to the fixed point. And so that satisfies the criteria for QAS. We can also see that if we start within delta, we stay within epsilon. So that satisfies the criteria for LS. So both of those together gives us AS. So the stable focus is AS. Second example here is a center. So, well, clearly it's Lyapunov stable because you can just choose epsilon equal to delta. Yeah, well, in this case, right, we've just drawn the center as a collection of circles. I mean, they could be ellipses, or they could just be deformed closed loops that do not intersect. And I guess the way you can argue that, if it's true for this center that is drawn very nicely, and then it's also true for centers that may have just arbitrary shaped closed loops. The way you would argue that this argument applies to that as well is the concept of topological equivalence. So, well, I'm not really a pure mathematician, but I guess in simple terms, if you can continuously deform these contours into just arbitrary, non-intersecting closed curves around a fixed point. And so if this thing is LS, then it's LS no matter how you draw the orbits, the cycles, sorry. Does that make sense?
So is there some theorem that says Lyapunov stability is topologically like a...
I mean, we didn't do this in lectures, but we did talk quite a bit about topological equivalence and how properties in general do carry over. So I think in the scope of the course, they do kind of just carry over, because we're taught to transform systems into forms that are more easy to work with and then transform them back. So I think it's just assumed that within the scope of the course we can do that.
Yeah. Okay.
Yeah. Yeah. So it's quite simple. This is actually a theorem, although I haven't written it as a theorem. And it's just about the stability of various fixed points, including hyperbolic fixed points. So just recall that hyperbolic fixed points are fixed points such that the real part of the Jacobian eigenvalues are non-zero, as in like none of the eigenvalues have real part equal to 0. So recall that these are the possible hyperbolic fixed points. We have node, focus, and star nodes, and also improper nodes. And we have the unstable counterparts of those. And we also have saddles, which are stable in one direction and unstable in another direction. So for the overall stability of the fixed point, if all of the eigenvalues of the Jacobian have real part greater than or equal to 0, then the fixed point is asymptotically stable. So that is these 3 cases, or 4 if you count these 2 as different. And if, on the contrary, there exists even one eigenvalue with negative real part, then it is just unstable. It's not LS, it's not QAS, and it's not AS. Yeah. You're familiar with like star nodes and improper nodes, right?
Yeah.
Okay. Yeah, so I guess the key thing is just, if there is an eigenvalue of negative real part, it's unstable. Otherwise, it's asymptotically stable. And this applies to only the hyperbolic fixed points. Next we'll move on to Lyapunov functions, which is kind of, this is the meat of this section. This is what is important. The rest of it was kind of background theory to lead up to this. So we're going to define a Lyapunov function for an initial value problem x dot is equal to f of x to be, firstly it's C1, so it's continuously differentiable. Secondly, it's going to map from Rn to R, and it's going to be on a domain D containing neighborhood of 0, which, we're assuming here without loss of generality that the fixed point is at the origin, because we can just recenter the system. So we must have, so this is the criteria for it to be a Lyapunov function. We must have that v at the origin is equal to 0, and v of x is greater than 0 for all x not equal to 0 in the domain. So so it's probably, it's 0 at the fixed point only. and it's greater than 0 elsewhere on the domain. The second thing is that v dot is going to be less than or equal to 0 in the domain, so it's non-increasing. And this thing apparently is equivalent. Which makes sense, right? And by non-increasing, I mean in time, right?
Yeah.
Well, clearly, I'm saying v is non-increasing. So I guess that's why this is equivalent, because we're saying that if I start at some point x and I go forward in time, then the v evaluated at that new point will be less than or equal to the original v, because it's non-increasing. Yep. And a little note, we call the Lyapunov function a strict Lyapunov function if in this part 2 bit we have strict inequality. And that gives us, well, it's a stronger condition, obviously, so it gives us a stronger result. And we'll see that in L2, which is Lyapunov's second theorem. But for now, we'll look at L1. Sorry, water break. Yep. So Lyapunov's first theorem says that if there exists a Lyapunov function, well, for the fixed point at 0, then the fixed point at 0 is Lyapunov stable. So yeah, it's very simple, very easy to remember. It just makes a lot of sense. Yeah, Lyapunov's theorem tells you about Lyapunov stability. And yeah, we'll look at the proof for this. So, I mean, the idea of the proof, like the goal is to show that if there exists a Lyapunov function, then if we start within delta of, well, if we start within a circle of radius delta centered at the origin, then we'll stay within a circle of radius epsilon centered at the origin, right? Because that's the definition. So, yeah, the first step is, we have this Lyapunov function on a domain D containing a neighborhood of 0, or origin, I should say. And so the first thing is to, without loss of generality, we can assume that epsilon is small enough such that this circle lies within, sorry, this disk, I should say, the disk lies in the domain. Do you understand why that's without loss of generality, right?
Yeah.
Yeah, good. The second thing is, now we're going to do something clever. We're going to set m equal to the minimum value that v takes on this circle of radius epsilon. So yeah, that's just going to be at a point, obviously, because the minimum value is actually realized on the circle. So that's going to be this purple thing that I've marked. And we can now extend this to this region, this region that we call C subscript m comma epsilon. That is just all of the points within the disk of radius epsilon, such that the Lyapunov function is less than m. So yeah, because it's strict inequality, we're just looking at the region that's enclosed by this curve.
Mm-hmm.
Yeah. Now we're going to choose a delta such that essentially we can draw this circle entirely within C m epsilon.
Yep.
I think that doesn't require much further explanation. And now we're going to justify why this construction shows that we have Lyapunov stability. So, well, it's quite simple, really. We start with x in the delta circle, or disk, I should say. Sorry about the language. So this implies that clearly we're within C m comma epsilon, which, as we defined, is going to, v evaluated in this region is going to be less than m, which means and so this is like the clever bit. This is from the definition of the Lyapunov function. This is the equivalent definition of the second bit, if you remember.
Yeah.
Yeah. So from that, we can now write that because like if we take the forward flow from x, because v is non-increasing, this thing is going to be less than or equal to v of x, which is less than m, as we said in the previous line. And so therefore, because it's less than m, we're going to be inside of this region, which means we're also inside of the epsilon disk. So we have this, which means that for all forward time, the flow stays in the epsilon disk, which is the definition of the Lyapunov stability.
Okay, can we go over that last step one more time? I just didn't quite get it.
Oh, which bit? So from here?
Yeah.
Yeah. So, well, this comes from a definition, the highlighted part, right? And we've just said it's less than m from the previous line, which I think you followed.
Yeah.
So because it's less than m, and we defined this region Cm epsilon. So remember, Cm epsilon is actually like the region inside this curve. We defined that to be the region where the Lyapunov function has value, is evaluated to less than m.
Right.
And we know that this Cm epsilon region lies entirely within the epsilon disk.
By definition. Yeah.
Yeah, because we defined it to be, yeah.
Yeah.
So I guess we should add an extra implication here that says that, yeah, so we should say that this flow lies within, I don't know why I've used in like this, it should be subset. Does that make more sense?
Yeah, that's, yeah.
Yeah. So you can kind of see why that's true, I guess. But the main step is this, which then implies that, yeah, we have to be inside of Cm comma epsilon because we defined it to be all of the points with v evaluating to less than m. That's inside the disk.
Mm-hmm.
Yeah. So that's the proof. I believe this is actually the only proof that you need to know from this section, because we're going to do the Lyapunov's second theorem in a bit, which the proof isn't strictly non-examinable, but it has never appeared in a past paper. Yeah. So I'm just guessing, and also the lecturer didn't go through it entirely. He just did a proof sketch, so I don't think it's examinable. And we also have Lassalle's invariance principle, which the lecturer did say was proof non-examinable. Okay, but anyway, the Lyapunov second theorem, as I said, because a strict Lyapunov function is a stronger result, we're going to really get a stronger consequence. So in fact, if v is a strict Lyapunov function, then, well, sorry, on a domain containing the neighborhood of the fixed point at the origin, then the origin is asymptotically stable.
Yeah, this makes sense. So you strictly decrease into the fixed point.
Compared to just, the Lyapunov stable. Okay. Next thing, we're getting to the end. Lassalle's invariance principle. So this combined with Lyapunov's theorems, this forms the basis of like all of the methods that we use to tackle any question on stability, really. So yeah, Lassalle's invariance principle is about the existence of invariant subset. So it doesn't tell us what the invariant subset is, it just tells us that like one exists in a certain region. So yeah, if v is a Lyapunov function on a compact and forward invariant domain D, compact, closed, and bounded, forward invariant just means if you go forward in time, then you stay within the domain. Then that implies that there exists, sorry, I should really write there exists. So there exists an invariant subset omega of x. It's a subset of this complicated looking thing that just says, yeah, I'm not sure how to put this into words. It's just all of the points such that, if you evaluate the Lyapunov function at any point in the forward flow of this point, then you get the same as the Lyapunov function evaluated at a fixed point. Yeah, it's a bit hard to put into words, but as a notation. Yeah, and the main point, is there is an invariant subset. It doesn't tell you anything about, what it is, how to find it. It just tells you there is one in this kind of area. And yeah, that's not very useful, but there's a useful consequence, which is, if there exists an invariant set, then we must have that this flow, we must have that any trajectory is going to tend to the invariant set, right? And that means that the invariant set is going to be in this region. Right. So therefore, if v dot is not equal to 0, then there doesn't exist an invariant set in the domain.
Right.
We can use this result to rule out the existence of an invariant set.
Because if there's a point where the v dot is 0, then that is a point where it's the Lyapunov function is constant on the flow, the forward flow from that point. So you're in that set with the blue annotation.
Yeah, exactly.
Okay.
Yeah, so that's a useful result to rule out invariant sets. We'll see very soon how we can use Lassalle's invariance principle to, detect an invariant subset, and then we'll pair that with the Lyapunov theorems to show what the invariant subset must be. But first we have to define the domain of stability, which is quite straightforward as what you would expect. Domain of stability of an asymptotically stable invariant set, lambda, is just all of the points such that the forward flow tends to the invariant set.
Yeah.
It's just what domain is it stable on? Does it attract in? Yeah. And globally stable is also quite intuitive. Well, yeah, if you're attracted to the invariant set from any point in your space, then it's globally stable.
Yeah.
Yep, so now we've defined that, we can go on to the method outline. You'll see a lot of kind of tripos questions where they say, show, like, classify the stability of this point, like, describe the behavior, blah, blah. So the first thing you do is you use Lyapunov's first theorem to show that your fixed point is Lyapunov stable. And so by doing this, now you want to show that it's the only possible invariant subset. So, well, this is from this thing is from this. So if we solve for the points such that v dot evaluated at the point is equal to 0, then you should be able to show that the only point where that's true is 0. So you'll show that 0 is the only possible invariant subset. You haven't shown that it is an invariant subset yet, because remember, this is a necessary but not sufficient condition. Because it's a consequence of Lassalle. Yep, so once you've shown it's the only possible, like it's the only candidate for being an invariant subset, you now invoke Lassalle to show that there is an invariant subset in the region, right? Because if you have one possible invariant subset and there has to be one, then clearly that your one candidate is actually an invariant subset, right?
Right.
Yeah, so you use LaSalle, and you just show that in the domain that you're working on with your Lyapunov function, like you should choose one, or the question will give you one. You show that the domain is compact and forward invariant, and by LaSalle's invariance principle, that tells you that there is an invariant subset in the domain. So yeah, because there is one and 0 is the only candidate, the invariant subset is equal to the set consisting of just the origin.
Yeah.
Yeah, so then you would say now that the origin is asymptotically stable. Yeah, it's asymptotically stable with domain of stability D. Yeah, and there's kind of a note. You can optimize your Lyapunov function. I mean, optimize in the sense that by changing your Lyapunov function, you can get a smaller domain, a larger domain of stability. So you can say more about the behavior of points further away, the trajectories from those points. And you can do that by adjusting a parameter. So usually the question will suggest this, for example, well, the parameter a here, or a squared. Lastly, we have boundary functions. So these will tell us, it's more like a bigger picture thing, actually. So you'd probably use a boundary function first, and then you do something with Lyapunov and LaSalle. So a boundary function is basically something that will tell you, it tells you that, all trajectories eventually have to enter some region and get trapped in there. So a boundary function is a function v with bounded contours. In other words, the curves of constant v are bounded, and v dot is less than some negative delta, which is less than 0, for v greater than or equal to m. And so I don't know why I've written this differently. I should probably say this is m, capital M. So yeah, so the contour, right? This is the contour v equals to m. So it's just a closed curve where your boundary function evaluates to m. So if v dot is less than negative delta, less than 0, outside of this, then all trajectories are going to eventually enter this region. And that makes sense, right? Because, well, v is continuous. And so if we start outside and v dot is negative, then clearly we're going to go into this region. Yeah. And yeah, I guess the remark is, I'm not going to go into terrible detail with this, probably just want to do some questions. But after you determine that the trajectories get trapped in some region, you can then analyze, whether there's an attractor in that region, what the domain of stability is, and so on. Yeah, and I guess once you determine they go into this region, you just have a smaller area to work with. Yeah, that's everything in the whole chapter, minus a few examples, because yeah, I think examples were already fine and lectures. So this is just material with extended explanation. Do you have any questions?
I do not.
Well, okay. Well, that concludes today's discussion.
Okay.
Yay. Wonderful. How do I stop recording? It's going to end up
Good
the
evening.
reel. Ah.